Yeah, break was pretty good. Went down to Arizona. It was below 100, so it was pretty comfortable. Went out with friends at night where the low was like 86 degrees and they're all wearing jackets. You gotta love people in Arizona. All right, residuals. This is basically what a residual is. Line of best fit. Still with me? You could have a dot above or you could have a dot below. Agree? Yes, there could be a bunch of other dots on there. Agree? The residual basically is the vertical distance above or the vertical distance below that your data point would be. Want to know it's nice? Desmos does it for you. Okay, so let's make sure on Desmos we go through and take a look at it. So basically the residual is the observed Y value over the predicted Y value. The predicted Y value you get from your line of best fit. Uh-oh. Someone already getting a Starbucks gift card. It is you. What'd you do? Good for you. I hope you want to bless it. You know, you can always say, I need to go to Stirrups for him to get help with Stirrups. For him to chill here.
All right, we'll do that.
What period is it? Fifth?
Your advisor.
I'm here.
Oh, yeah.
You gotta show up though. You can't just be like, Stirrup, I'm sure. I know you. All right, so if I have something above the line of best fit, it'd be a positive residual. If I have something below, it'd be negative. Okay, it's just the vertical distance above or below. Again, Desmos was built for you, so let's make sure we know how to do it. So the equation is observed Y minus predicted Y. So they have the weird notation where they have R equals Y minus Y hat. Remember, Y hat is from the line of best fit. The line of best fit is what you would use to predict. The data values would be the actual data that is plotted. Positive residual occurs when the predicted value is less than the observed. Okay, negative occurs when the predicted value is greater than the observed. Zero residual means that your point fell right on the line, your example. All right, so let's talk about this next one. I need to go to Desmos. Let's make sure we know how to do this on Desmos. Okay, so the first thing it's going to tell us, move down a little bit, is so we could do this whole equation here, which is basically meaning I'm taking this Y value here, this 5, plugging it in or plugging this X value in for the X, and then sorting it out. But that's like arithmetic. I have a point, I have an equation. Agree? So I'm going to plot the equation. Don't worry about doing Y hat. This will just be a Y equals 2.5 and then plus 1.5x. So do you think it really matters? Do you think it matters if I had 1.5x first plus 2.5? Or does statistics just kind of flip-flop because statisticians are big jerks? You say they're big jerks, you're right. All right, so that's my line of best fit. Everyone agree? Now, we don't really have data. This is our predicted line. But what I can do is if you hit the positive, you make a table, plot the point 3, 5. Okay, so notice I have this dot that seems to have a vertical distance, looks like it's about 2 from the line of best fit. Well, the nice thing is you have that data. How can I find my residual? Let's see. I don't want to do that. Oh, I wanted to do it so much differently. So let's just take this into account. Let's plot this point. Let's make another table. I'm going to use this other table. So I know that I had an x value of 3. Where do you think this appears on this line right here? 3, 3, 7? Okay. 3-7. Okay. So how far do you think those 2 points are from each other vertically?
2.
They're 2. Is the original point that we had plotted, the green point, is it below the line or is it above the line? Below. So it has a residual of -2. So notice I created 2 tables out of it. But there are definitely things that we could do. You know, if we weren't able to figure out that exact point, we could also do this. If I went, let's see if this is going to work. 2.5 plus 1.5 times 3. Yep, it still worked. It found us that value. Okay, so you could sometimes just count the residual easily. If we have a whole bunch of data that's plugged in there and we found a line of best fit using y hat, it's going to allow us to find the residual. The reason we can't find the residual right now is because I didn't plug data points in to get our line of best fit. The line of best fit was given to us. So we're looking for a vertical component. Because it's below our line of best fit, it's negative. If it happened above, it would be a positive. If it was 0, it means that our data point fell right on the line. Okay. Does that make sense? So things to know. The residual is kind of like an error. You gather a whole bunch of data, you plotted it, you realize, oh my gosh, a line of best fit is going to work. A line of best fit won't capture every point, but it's going to figure out what the line of best fit would be for you, rather than you trying to decipher, 2 points. Like in Algebra 1, what we used to do with this is you take the 2 furthest away points from in your data set that would fall on your line of best fit, and then find the slope, and then use point slope and solve it for slope intercept to find it. Again, Desmos does it really nicely for you. Okay, so talked about the calculators. Let's not go there. But on the back side, it says, why are residuals so important? So understanding the relationship between 2 variables is about building a model, a regression equation. Allows you to predict one from the other. Understanding why a model is making errors may help you understand the relationship between the variables better and even build a better model. Okay, so correlation is that R value. And we always equate that R value of, if it's positive or negative and it's close to 1 or close to -1, they're really good lines of best fit. Obviously, if you have 2 data points, you're going to have a perfect line of best fit because you all took geometry at some point, and you know that 2 non-distinct points will form exactly 1 line. But the more data you have, the more likely it is going to be that you're going to have the best line of best fit. 1 data point might change how the pitch of that line of best fit falls. So there just might be things that you start thinking about. If you are truly collecting data, now the hard thing is you're not going to go, unless you're in a class, but a bunch of data would happen. But if you were to try and collect data and you made it yourself, you want thousands of data points. Yes, in the world of statistics, they say 3 data points is adequate, but, or did I say 3? 30 is adequate, but you got to make sure you have enough. Like, did the points you find, were they coincidental or did they actually happen? Based on it, you didn't do any of that silly stuff. So there's an example. Let's say you have a system for predicting the winners of NFL football games. Ooh, that might be good for fantasy league. Hypothetically, you say that the system predicts winners correctly 70% of the time. If you want to improve your system, you will need to study the errors you're making. Is there something you're missing? Maybe discover the understanding of the teams in a certain division consistently. Understanding the pattern in your errors will allow you to adjust and potentially build a better model, which is basically like, why do I keep getting these data points? They fall in this. What other lurking variables might be impacting your data collection? So you do not need to know about the sum of squares. The sum of squares is basically taking every data point minus the predicted value, y value, squaring that, so it'll always become positive, and then summing it all up. This equation looks small, but it's got a lot of work to it. So I would not have you do that. It says overall the lines can be drawn through the scatter plot and linear regression. Equation always produces a minimum possible value for the sum of squares. An interesting visualization is shown on the next page. Okay, so sum of squares. Notice I have squares on this graph. Agree? So basically, what your calculator is doing is it takes a vertical component, makes a square out of it, a square where the length and width are the same, and you sum it all up, sum up all those areas, and then you take the square root, and that gets you the correlation, the R value. Okay, the R squared value is if you sum up that whole table. But it's basically a good way, but also a confusing way of trying to look at data. I mean, the bigger the box, the further it is away from your line of best fit. The smaller the box, the closer it is to your line of best fit. Okay, again, the line of best fit, the equation is used to predict, see when things will take place. Okay, so it says, as you can see from the display, the sum of squares from the regression line, sum squares is 14,310. There's no other line that would produce a lower sum of squares than the least squares regression line. So if you ever hear a term saying least squares regression line, it's you have data plotted, a line of best fit was found, correlation was found, correlation just being R. If you square that, that becomes the average area of how far your data is using a square, where length and width are the same. In the diagram, each residual square is represented by the area, and it says of the red square, but we only have black and white, so it didn't work for us. The total area of the square is called the sum of squares. So you might hear the sum of least squares, residual, things like that. There's all types of terms they use. It basically just means that you have a line of best fit, you have data points. So let's go back to this XY axis. Let's create a line of best fit. We'll make it green. And then we're going to sit there and we're going to have these data points. Each one of those data points has a vertical component to it. If I square it, I make a square. So if I could make squares, I'd be a much better person. Sorry to let y'all down. So it's basically making a whole bunch of squares, adding up their area. If you add up their areas, you know, when you plug your data in, you get the R squared value. The R squared value is the sum of all those squares. If you square something, it's a positive number. If you take the square root of it, it then becomes the correlation, or the R value. And again, the R value is used when we are talking about a straight line. It doesn't come into play when we are using, you know, a parabola or something like that. When you use a parabola, you actually use the R squared value, which is the sum of squares. And it's just basically a way to say, hey, we have a margin of error that's taking place. It's a type of error that's taking place. You know, if I had a data point, say like way down here, this would be like, well, what's going on right there? Why did that data point, give me that far away from my line of best fit? Did I, was it supposed to be 23,6 and I accidentally put 2.3,6 in? Well, hello. She saved your spot. I moved the room around because I'm a little psycho, but it's good to see you. Nice break.
Yeah.
So again, what we have planned for this week is I'll teach you 2.7 today. We'll do 2.8 tomorrow. Wednesday we will do the review. Thursday I won't be here, but you'll do the quiz all together. from 2.1 to 2.3 or 2.1 to 2.4, I think it is. Excuse me. Or 2.1 to 2.5, I don't remember what it is. It's something there. Also, a reminder, friends, your quarter grades went in. Your quarter grades mean nothing, okay? They don't show up on transcripts or anything like that. Your quarter grades will continue in this class, though. So if your grade isn't quite what it should be, go back and take a look at your grades. Do you have any zeros in there? If you do, take care of those zeros. Show me. I'm happy to put stuff in for first quarter. But make sure those are good because, excuse me, your semester grade is the one that the transcripts see. Okay, yes, auto insurance sometimes is like, oh, we want to take a look at your grades, so you give the quarter grades. But back in my day, they used to hand us the quarter report cards to go home with us. Mine never made it home. And I would tell my parents that they're trying to save trees, so they didn't print them. I'm pretty sure I fooled them well. But I think we're pretty good here. I think we're set. So welcome back. It's nice to see you, friends. Let's have you work on 2-7, which we'll go over tomorrow. So 2-7 will be your assignment for tonight, okay? What page does 2-7 say? How much? What? Page 157, thank you. And that's on off.